Here is the recipe for taking the implicit differential. You can take a look at that if you want to refresh your memory. Now let's do some examples together. Here's the first one. I'd like you to try it on your own. See if you can find the implicit differential. Press pause on your video, try it yourself, and then when you're ready, press play, and we'll work through it together. So the question's asking us to find the implicit differential. So I'm going to do that. I'm going to take the derivative of both sides. And when I do that, I'm going to get 2xy prime plus 2y is equal to 0. And I get y prime is equal to negative y over x. Notice that we could have rearranged this first, and so we could actually write y as a direct function. As a direct function of x, and I can write it, make it easier on myself and write it like that. Take the derivative, and we're going to have this expression right here. Presumably they will give us the same answer if we plug in the x's and y's. But remember, the question asked us to find this one, and so it looks like the right answer is E. Here's another problem. Again, I recommend that you press pause, try it yourself, find the answer, and then press play, and we'll go through the answer together. Now I want to take the derivative of both sides of this expression. Remember that y, we could actually think of y as some function of x. So if I did it that way, I would replace the y and carrying on. We take the derivative of both terms. And so we're going to end up with 4 f of x, f prime of x, plus 2y, plus 2x. Oh, I guess I should replace that y with an f of x if I'm going to do it this way to be consistent. And then we've got f prime of x multiplied by 2x, and this whole thing is going to be equal to 0. Now I want to solve for my f prime of x, and so maybe I'll just rewrite this expression like that, and I'll move this term over to the left-hand side. And now I'm going to divide this expression by both sides of the equation. So I get f prime of x is equal to negative 2 f of x over 4 f of x plus 2x. And I could simplify this a little bit. I've got a 2 in the numerator and a 2 in the denominator, so I could rewrite this as x over 2 f of x plus x. And what I should really do is I shouldn't really write y as a function of x like that, I should have it as y prime is equal to negative y divided by 2y plus x. Here's an example that's going to be very important to you in Econ 1530, 1540, and definitely in your second year microeconomics classes, and for that matter, third year and fourth year. We're going to look at a two-period model of consumption where consumers are enjoying utility based on how much they consume. There's only two periods, so you either have to consume today or consume tomorrow. You don't want to waste any consumption. That's not optimal. So you're going to either consume today or consume tomorrow. This is a powerful, neat little model that gives us a lot of intuition on human behavior. Because we know that people are impatient. People are by nature impatient. You might have noticed this in yourself, perhaps. That you would, all else being equal, you would prefer to have something good today than to wait and have it till tomorrow, all else being equal. People prefer things today. They want to have fun today, don't necessarily want to wait a month to have fun. And so we capture this with this beta, which you can see in the expression here. And I'm going to come back to this, this function that we have and talk about what it means in a minute. But before we talk about that function, I want to point out to you that how much you consume in the future depends on how much you consume today. So for example, if you think of yourself in this model, maybe you just have a fixed amount of income, and then you're going to choose how much to spend today, how much to spend in the future. Therefore, your spending is equal to your consumption. If you reduce your consumption today, that means you're saving more today. You're saving more of the total consumption you have available. And your consumption in the future is going to rise. So you're trying to decide, should I eat both pieces of cake that I have today, or should I eat one now and save one till tomorrow? Something like that. Right? Since how much you consume in the future depends on how much you consume today, we can say that consumption in the future is an implicit function of consumption today. So the choice that you make today, how much to eat today, is going to affect how much you're going to be able to eat in the future. Now let's turn our attention back to this expression here. Let me define each of the terms here. Now you know what the beta is, and maybe I'll talk about the beta as well. So to get started, we've got U. U is equal to total utility. So the total quantity of utility you get from how much you consume today and how much you consume tomorrow. U C1 is equal to the utility you receive from consumption today. And UC2 is equal to the utility you receive from consumption tomorrow. And that beta, that impatience, what we often call, it's most commonly known as a discount factor. But you can think of it as impatience. It is greater than 0, but less than 1. So it's going to be some sort of, well, I want to say fraction, but it could be, an irrational number as well. but it's going to be greater than 0 and less than 1. Typically, a common beta value would be something like 0.95. That would be a normal number to sub into this expression if we wanted to work with numbers.